The reason we're having a talk tonight is there's a lot of different areas that people don't understand about, and one of them is about decarbonisation. We hear a lot about talk about energy, we hear a lot about talk about zero carbon, net carbon, carbon emissions, and when it all boils down to it, it's a very confusing subject. And so what we're going to try and do with these different talks we're going to have is actually just to inform people, so to try and be unbiased and give information so you can actually make up your own mind on different things. So tonight we're going to have a introduction. I'll go through limitations, talk about greenhouse cycle. We'll have a crash course in renewable energy, all the different types, the main types. We'll talk about nuclear, carbon capture and storage very briefly, and we'll have a Q&A at the end. The main three areas I'll talk a lot more about is going to be solar photovoltaic. It's going to be one of the main technologies in this country and around the world. Also wind. So wind is going to be one of the main technologies, it already is in this country. So I'll talk a lot more about that. And some of the other ones I'm just going to skim through very quickly. Just to give you a little bit idea of my background. I was a surveyor, and about 2004, 2005, I was doing stuff with Friends of the Earth, and I went to the Big Ask campaign, and it was to get the British government to declare a climate emergency. And going to these talks was very influential, and I realised then that the work I was doing, getting people to voluntarily switch off lights, wasn't actually going to, be enough, and that the actual whole world needs to go renewable. So I went and I left my job, went and started working for a company doing heat pumps. I realised all the people I was working with didn't actually understand the technology, so I went back to college. I did a master's. It nearly killed me. It was very technical, a lot of engineering, and a lot of things I didn't really understand. I went from a very soft subject to a very hard subject, and I set up a company, and I've worked in solar for several years in the United Kingdom till the British government decided to get rid of all subsidies for solar, subsidies for onshore wind. They closed down Warmfront. There's loads of different things that happened. I won't go into it. Then since then, I've worked on international projects. I've also worked abroad in quite a few European countries doing education in renewable energy. So bringing people from the UK, electricians and plumbers, and bring them to Germany to train them up and installing solar heat pumps and solar thermal units. So I'm going to try and condense everything I know into an hour and a half. Greenhouse gases and global emissions, we hear quite a lot about this. The main greenhouse gases that we've got, they come into two categories. The first ones we've got is carbon dioxide, methane and nitrous oxide, which are the main ones that are emitted from fossil fuels and agricultural use and fertilizers. Then we've got four different F gases, and F gases are man-made gases, and they're used in refrigeration. They're also used in electrical circuits. These are the ones that are actually counted. So according to the Kyoto Protocol on greenhouse gases, so greenhouse gas accounting, these are the ones that are actually accounted. And the lion's share, as you can see here, is carbon dioxide, which is 76% of the greenhouse gases is carbon dioxide. And all the different greenhouse gases, they all have completely different characteristics. So you can't compare like for like because of the chemical compounds. So what we've got here is, just to give you an example, we compare everything. It's down to the global warming potential. So carbon dioxide is a very, very weak greenhouse gas. So when the sun hits the earth and then bounces back into space, carbon dioxide traps like a little tiny fraction of heat. But compared to other greenhouse gases, they're a lot more potent. CH4 is methane. Over 100 years is 28 more times potent of stopping greenhouse gases. Right, and then we get to all the way down to the man-made gases, sulfur hexafluorides, and it's 23,500 times more powerful greenhouse gas. You'll hear things of F-gas regulation. So if you hear about F-gas, this is what they're talking about. They're talking about man-made. So in terms of parts per million, we can actually work out in the atmosphere how many parts per million we've got of different gases. And as I said, the lion's share is carbon dioxide, and carbon dioxide predominantly comes from fossil fuels. These are lovely fossil fuels: coal, oil, gas. Different fuels that you hear of that are fossil fuels will all relate back to one form or the other. What's the problem? Well, the emissions from fossil fuels are literally skyrocketing. We are addicted to hydrocarbons. The amount of energy that they give us has created our society that we live in. It's created our the houses that we have, the cars that we drive. Everything that we've got is owed to hydrocarbons, and we're now understanding the actual costs and the problem of burning fossil fuels. So what we need to do is greatly reduce fossil fuel to pretty much zero. This is the pain that we have to go through. We can actually measure in the atmosphere exactly how much carbon dioxide, CO2, is in the atmosphere. We're at now, I think, 416 parts per million. This is like nearly double what it was. CO2 has been constant in the atmosphere for about 3 million years. We know that from taking samples in ice samples, and you can see exactly how much carbon was in the atmosphere. And then you can see, trundling along, we hit boom times, we get really good at extraction methods, population explosion, and all of a sudden, it's going through the roof. Not only CO2, but also methane is rising as well, and also F-gases are rising. A quick crash course in carbon cycle. What we've got two different carbon cycles. We've got the long carbon cycle, and we've got the short carbon cycle. So the long one is where coal, oil, gas come from, and it can take hundreds of millions of years for coal to form. Over millions of years, it gets sucked out of the atmosphere through trees, all different forms of life, and through millions of years, it compresses and forms fossil fuels. That's why it's called fossil fuels. So what we're doing is we're extracting the fossil fuels and we're releasing it into our short-term carbon cycle, which is over here. I've got two different charts here. This one here is taken from David McKay's book, which we had to read going to college about 12 years ago, which is an absolutely fantastic book. I highly recommend reading you can actually get it online, you can download it for free. So when he was talking about it, you've got some difference of figures here. You got in the atmosphere, you got 600 gigatons. In a more recent one, it's 800 gigatons. That's because of all the fossil fuels we've recently burnt. So we can measure exactly how much carbon is in different places, carbon dioxide. And what's happening is we're upsetting the balance. So when we burn fossil fuels, we burn carbon, it goes into the atmosphere, and naturally the oceans and the soils and the forests absorb vast amount of it, and then there's a little bit left over, and that's what we're having, like the 416 parts per million. It's increasing ever so slightly to a devastating effect. Whatever's in the atmosphere, we have this area just here that the near surface in the sea, it actually balances. So there's a slow cycle that it will actually catch up. So if you have 416 parts per million, a similar amount ends up here in near surface. Then in the deep parts of the ocean, it actually takes hundreds and hundreds of years to actually filter down. So there's almost like it's a barrier. It's almost like a concrete barrier that it can't go through. And we've, as humans, have now upset this natural cycle. So this is why we need to actually, not only do we have to stop burning fossil fuels, we have to figure out ways of decreasing the amount that's actually in the atmosphere. At the moment, we're burning through our annual CO2 emissions. Actually, this is all emissions is 52 gigatons a year. That's including methane and the other greenhouse gases. We could be even increasing it at today's rate. We need to halve in the next 10 years is what we need to do. And by the mid-century, we have to actually have totally stopped burning and extracting all forms of fossil fuels. So this is where we need to get to. This is where we're here. And the question is, how are we actually going to do it? At the moment, to give you an idea, with renewable energy, at this moment in time, just 4% of the world's energy comes from renewable energy. We've got another nearly 7% from hydro. It's accounted differently to renewables. It is still it's still renewable energy, but it's counted different. So if you add this and renewables together and nuclear, it's about 14-15% of the world's total energy demand. So we've got a huge amount of work to do, like absolutely colossal amount of work. It's just, yeah, it's a little bit scary really. So today's talk is, I'm focusing on one part of it, which is decarbonising the grid, and it's decarbonising the electrical grid. So we've got several different types of grids. In this country we've got a gas grid where we heat our homes, and we have the electrical grid. All right, so this is a picture of the control room that you have in the National Grid Centre. It's highly complex. You're going to have like a big energy source, like a nuclear power plant or a coal fire plant that produces vast amounts of energy. Then you have substations, you have transformers that step up the electricity, they step down the electricity, they get it into high voltage so it can travel long distances, and then it gets to your DNO, your local distribution network, and it steps down again into a medium voltage, and then it steps down again into a voltage like 230 volts or 400 volts that you can use in factories, and you can use in your houses. So it goes through a process. While it's going through this process, it uses a lot of energy at the start. There's a lot of wastage around this area. When the energy is getting transmitted, there's also more wastage. And then by the time it gets to us, there's even more wastage because we leave lights switched on. So there's the whole system itself has like huge amounts of wastage to it. To give you an idea where we are now in the UK, this is 2008 when the Climate Change Act got announced, which was quite amazing. What you see here is you got the actual energy for the whole country being used, and you can see it's on this nice decline that's going down. So from 2006 to 2019, we've seen this nice slow decline. So we need to continue reducing the amount of energy consumption. So that's LED lighting has reduced the amount of energy, and people becoming aware of actually not wasting electricity, and also a lot of processes that we do is getting more and more efficient. What you got here is coal. As you can see, coal is actually starting to phase off, because one of the easiest ways of decarbonising the grid is to get rid of the dirtiest form of energy, which is coal. So when you burn coal, it's a lot dirtier than burning oil, and oil is a lot dirtier than burning gas. So they release different amounts of carbon into the atmosphere. What we've got then here, this is natural gas, which is pretty consistent. For the future, they're still going to be relying on natural gas, looking at the different papers that have been released by the government. Then we have nuclear, which tapered off a little bit, but we're going to have a lot of nuclear getting decommissioned, and there's a lot of nuclear coming back up online. And then all the way down here, this little grey area here, that's starting from nothing and starting to get like as you can see, it's growing in size, is renewables. And that's a mixture of wind, onshore, offshore wind, and solar PV mainly. And then we've got bioenergy, which is a little bit of a grey area, because a lot of bioenergy in this country is actually, it's waste. So we're actually energy to waste, but it's counted as a form of energy. And we've got some pump storage, and then we've got interconnectors that we get electricity from France, from Ireland. We get to share the grid, so at peak times we get to have extra amounts of energy. So to give you an idea, last time I did this talk, the amount of CO2 that we had, the current carbon intensity of the grid was 203 grams of CO2 per kilowatt hour. So in 2013 to 2017, we've managed to decrease the carbon content of our electrical grid by nearly half, which is quite amazing. So the electrical grid is actually doing very well decarbonising. The gas grid is not being decarbonised at all. Transport's not being decarbonised at all, and agriculture. Don't just take these figures that we're actually doing pretty well. So you can see here the mix at this time. You had wind at 14.2. There was no solar. I'm just going to skip ahead to today. I took this screenshot a couple of hours ago, and you can see we've just had a storm, and 27% of all the electrical energy in the United Kingdom is being produced by wind, which is actually which is quite amazing, And then also, you mightn't think it, we've had a 6% by solar today. combining, 27 and 6%, 28, so you got like 34%, so over a third of our electrical grid today was being produced by renewable energy. So that's quite good. We've got a hydro who's topping us up a little bit. We've got nuclear, which is a base load. It's very hard to switch on and off nuclear power plants, so there's always a base load of electricity coming from them. We had some of our imports. This is the interconnectors coming in here. We've still got coal on our grid, which is quite dirty. So the current carbon intensity was 155 grams per kilowatt hour compared to 203. So you can see it actually varies quite a lot. So, you can see here that we're actually, we're getting in the right direction for renewable energy, but we're not getting there quick enough. Okay, so main area to talk now, I'm going to be talking about the different types of renewables. Renewable energy is it's energy generated by natural resources that can replenish itself quickly, and quickly is within our lifetime. All right, so certain ones like certain types of fossil fuels that are quick growing is like peat bog. It can grow in a couple of 100 years. You can get peat bog growing and absorbs lots of carbon. If you burn that, you're not going to hang around waiting a couple of 100 years to replace it. So the main types we've got is three main sources. We've got this big huge ball in the sky called the sun that emits vast amounts of solar radiance. Most of the renewable energy that we have comes from the sun. The other types we have is geothermal energy, and that actually comes from the core of the Earth. So when the Earth was formed 4.5 billion years ago, there's lots of like mini nuclear reactors still kind of going on in there, and so you got all this heat in the crust. You can actually use that energy from deep geothermal, and then we've got this wonderful body called the moon that spins around. And we've got this gravitational pull with this huge body of water that gives us tides, and that gives us tidal energy. So in terms of the amount of energy that we have that's being replenished on a yearly basis, give you an idea, we've got hydropower. So if the whole world relied on hydro, we could meet all the energy needs of the world. It's not going to happen because there's lots of technical difficulties. We got wave and tidal. If we could harness all that, it could give us everything we need for 1 or 2 times. Geothermal is 5 times. Biomass, which is trees and anything that we can burn and regrow, it will give us 20 times. And then we start getting onto wind. There's enough wind to give us 200 times more energy than the whole world needs, which is quite phenomenal. And then we get to solar energy, and we're at 2,850 times. So pretty much within about an hour of solar radiance hitting the Earth, if we could harness that, we could power the whole world. So the power of the sun. The main types that we've got is direct solar energy. You heard of solar panels. So that's solar photovoltaic. Solar thermal, it also direct energy from the sun. Heats up the hot water. Passive solar, if you've got a nice big south-facing window, naturally the solar energy will just heat up the room. Indirect, so indirect solar energy is hydropower. What happens is the sun heats up water, water evaporates, goes over a mountain, it cools down, it rains, forms a river, it flows down, you put a dam up, and then you generate energy from that. You've also got wind power, which is indirect. So the sun heats up the water and it heats up land, and you've got different temperature differences that happen, and the cold air moves into the warm air, and you get this nice big cycle happening, which creates all the wind. Bioenergy is again the sun through photosynthesis gets plants to grow. The plants grow, you chop the plants and you burn the plants, so it's indirect. And then we have the non-solar, again, deep geothermal, when you go into the core of the Earth and you harness the heat from there, and tidal energy. So we're on to wind, right? So I spent several years working on wind projects. This here is in Portugal, and here is me standing at the base of this wind turbine, which used to be at one point they had amongst the biggest wind turbines in the world. Quite recently, Portugal has managed to run its whole grid 100% on renewable energy. So a combination of wind and hydro and some solar as well. Again, it's quite amazing. This is Kilvarna in Bulgaria. You'll have a lot of wind where you'll have sea, and where you have land, and you have like onshore wind, offshore wind. Absolutely great place to actually harness wind energy. Some nice facts about the UK is it's one of the best countries in the world, and probably the best country in Europe for wind resources. It has a quarter of all the wind in Europe is in United Kingdom, British Isles and the North Sea. All we have to do is harness it. Wind power contributed 18% of electricity generated in 2018. From the slides that we showed earlier, we had wind and solar nearly 33% today, which is quite amazing. The cost of wind has come down so much with the technology improving and the height that the cheapest form of energy in the United Kingdom now is onshore wind. And offshore wind is catching up pretty quick. Wind is like surpassed coal. Coal is on its way out. Yeah, and it's also surpassed nuclear. Wind in this country is doing very well. How it works? It works through kinetic energy. We've got now a standard wind turbine. You have a horizontal post coming up. You have a generator on top with the standard design now is using 3 blades. Throughout history, we've had lots of different prototypes. We have like lots of different types of wind machines. We've had ones with 2 blades, ones with 5 blades. We've had ones that have been bladeless. We've got ones that are actually curved that can go onto the side of buildings. But pretty much now the standard one that's been designed is going up everywhere is 3 blades, and then you're attached to a generator. There's a gear shifts in here. The blades are going around between 10 to 20 times a minute. By the time it gets into your generator, this has gone up to about 2,000, between 1,500, 2,000 revs per minute, spinning like crazy to generate electricity. What you've also got then is you've got a little wind dial at the top here, and it actually measures the wind speed. So it has to wait for a certain wind speed for the turbine to start working. And the modern turbines that we have now are actually so large that they actually draw energy from the grid to start. Because of the weight, they actually need to draw a little bit of energy, and they'll start spinning to get up to speed, and then the wind will take over. What you have is you have the wind hitting the blade. You have some positive and negative pressure. So when the actual wind turbine is actually going around, the blades are actually they're like flying like an airplane. So positive, negative. You got some lift going on, and that's the energy. So kinetic energy. Here in the UK is the world leader in offshore wind. The largest wind farm in the world is the London Array. There's another one that's just gone up in the north of England, which is slightly bigger, and there's plans for even more. So, give you an idea of how large the wind turbine blades are going. They're now up to 107 meters in length. They're getting bigger, and the reason they're getting bigger is because the bigger the wind turbine you have, the more energy it catches, and it works on a cubed law. So if you've doubled the size of a wind turbine, you quadruple the output, and it's more efficient as well for the gear levers. It's cheaper for the cables. So economies of scale. So bigger is better, and also offshore wind. You get like a lot smoother wind when it's offshore, so you get better wind quality, and you also get better wind speeds. And in this country, they like offshore wind because you get less people complaining about them. To give you an idea of offshore wind turbines and the size turbines are going, years ago when I was doing this in Germany, we were looking at 6 megawatt Siemens turbines. They're bigger span than the London Eye. More recently, it's gone from 6 megawatts to 12 megawatts. This is being built in Holland, and you can see here it's not shy of the height of the Eiffel Tower. So between the size of the London Eye and the Eiffel Tower. You got one of these turbines. Its capacity factor is a lot greater because what happens is it can actually work in lower wind speeds, so you actually get more energy from the wind. The blades themselves on these ones, 107 meters long, they have to have a special coating on them, because the problem is when rain hits them, it hits them at such a speed with the blades going up that they have a special coating on them. And the blades themselves, it takes about 240 people to make one blade. So this is currently being built, and one turbine is enough energy for 16,000 houses. More things coming into the future. We're going to have floating wind turbines. The first floating wind turbine farm has opened in Scotland last year. It's got 6 turbines. The beauty about floating wind is as you get deeper into the ocean, you need to have more steel, more concrete, more cables, and more costs for actually constructing them. And then if there's a problem, you have to send a big ship out to try and fix it, which costs a lot of money. If you've got a floating wind turbine, what you do is you unhook it from the seabed and you get a ship and you bring it back to shore and you repair it and you bring it back out again. So floating wind turbines is something in the future that we can see quite a lot more of. We've got different designs going on. A lot of them are based on oil platforms for balancing the sea. In the North Sea, we've got absolutely grand plans for actually even building an artificial island. And you're going to have interconnectors between Holland, Norway, UK, France, Belgium, all going together to different countries. And the whole idea is to bring the cost down even more. You have a centralized place for all the wind turbines to actually, for the energy to go, and it brings the cost down. And again, you've also got then maintenance for the ships to come in and out, and you got the workers that can actually live on an island like this. With the wind potential in the world of enough wind to power the whole world 200 times over, it is possible. We have the engineering solutions to it. Countries are working very hard on it. Several things we do have to overcome, but they are happening. And it's a quite an exciting thing to see. In this country, again, they got rid of onshore wind. There's people complaining about them. If you ever heard the term NIMBYs, not in my back garden. People not liking the sight of wind turbines and pretty much killed onshore wind, which is a shame because again, onshore wind is probably about half the price of offshore wind. Summary, advantages: wind is never going to run out. It's cheap. It provides a lot of jobs, continuous jobs. It stops the reliance on imported energy into the country. And also it's actually a very efficient use of space. If you use wind turbines on land, you can actually still have sheep and you can still have farms underneath. It doesn't actually interfere. And you can even have a forest underneath. So you can actually have wind turbines and it doesn't upset land use at all. Biggest disadvantage to wind is it's an intermittent supply of energy. So over Christmas, over winter periods, you get a lot more wind than you do in the summer. You get more wind at night than you do during the day. But wind doesn't blow 24 hours a day, so it's an intermittent supply. We can work out over a year, an average over a year, or over 10 years, how much energy we get. So we know how much we will expect to generate over 1 year, 5 year, 10 year period. So we can work that out pretty accurately using wind data and wind charts. And they've got wind atlases that actually tell you how much wind blows in different places. But it is intermittent, so it has to be balanced. So this is one of the main problems with renewable energy. It's getting the old system of having traditional constant amount of energy versus an energy supply that's intermittent. Apart from that is a high investment cost for wind turbines. Visual, as I was saying, on onshore wind, you have people complaining about they don't like how they look, and that's why they got rid of onshore wind in this country, pretty much was the main reason. Again, cheapest form of energy. Noise, they've got better at like stopping this. Sometimes if you have quite a few of them together, you get this certain frequency of noise. And there is a problem with birds, but surprisingly, the amount of birds that are killed compared to birds that are killed by cars, it's outnumbered. I think it's something like 50 to 1 or whatever. So there isn't actually as many birds killed by wind turbines as people think. When you're designing a wind farm onshore or offshore, you have to do a study to actually check where birds migrate. So you won't put a wind farm up where there's where there's going to be birds going across. Solar photovoltaic. I've spent quite a long time working in renewables, and most of the time I've spent is working in solar. Here's me happy on a roof in London. At my happiest is out and about lifting stuff and shouting at people and building stuff. It's always a nice thing to do. Si is the main ingredient for solar at the moment, which is sand, second most abundant substance in the world. You heat it to a very, very high temperature and you form crystals. And then over a very slow process, you get the crystals and you cut them using, it's almost like a form of thread. It takes about 24 hours to cut one solar cell. Each solar cell is thinner than a human hair. Got a little sample here you can have a look at. You can't see exactly how thin it is, but they all come in all different shapes and sizes. Historically, the solar that we've got now first came to use commercially in, I think it was 1956. It was a 1 kilowatt solar panel, and it was used in space to power a radio. NASA and space development have actually been developing modern day solar. Historically, solar has been used by the Chinese and different places around the world for actually reflecting it and using the sun's power to actually light fires. So it was the first use of solar, which is concentrated solar. Solar we're looking at now is solar photovoltaic, and it works by you have a positive and negative layer between the solar cells, and what it does is it excites the electron. The electrons form a current, and then the current gets captured, and that's what generates the electricity. As you can go into the physics of it quite a lot more, and people spend their whole lives going into it. I just know it from a very kind of overview of actually designing and installing systems. So what we got here is we got the you got the use in space here. You got the most expensive solar panels in the world, and then how versatile it is over here in war-torn regions of the world where there's no grid. You can put up solar panels and you can use it to run microgrids. So it's very versatile. It's transportable. You can bring it anywhere. You can install it anywhere. It works in the North Pole. It will work in mountains. It will work on ships. Anywhere that's a solar radiance. So we have a solar constant. The sun emits about, I think, 1,300 watts per meter squared of constant solar energy. Throughout the year, it changes just a little bit with the wobble of the earth. But we can harness that in lots of different ways. So much so that solar technology is exploding. We've got organic solar panels now. We've got ones that use thin and monocrystal together, so they actually form a plate, so to increase the efficiency. These ones here are monocrystalline, and you can tell they're mono because they're black, and polycrystalline. So 95% of all the solar panels, 97% of all the solar panels you see in the world are going to be one of these two types. And these are the standards. And then from here, they break down into different ones. We got bifacial panels that you can actually use energy from the backside, from the reflection of the albedo effect on the ground. You can combine them. You've got these ones here. This is thin film. It's about 100 times thinner than the ones I'm just passing around there. You've got ones now you can actually print. You can get ones that you got dye solar. You can get ones you can actually even manufacture into clothes. You've got ones that are clear. You can have glass that actually can be a giant solar panel, and you can get paneling, and it can look like metallic paneling, and the whole building can be solar. So solar is going to be the future. It is the future, and there's so many developments happening in solar that the price of solar is tumbling, and it's every year it's getting cheaper. Even the projects that we're working on at the moment, we put in a quote for a system, and 6 months later we have to update the quote because we've just been given cheaper solar panels and more efficient, from the same manufacturers, and they've gone up to like 390 watt. When I was installing solar, the first ones we're using were 190, 200 watt solar panels. So they've nearly doubled in size, and the efficiency's got better, and they've got cheaper. And we've got a lot cheaper every year. The price is just tumbling down. Give you an idea, since 1977, it's as far as back as I could find an example. you're talking about $76 per watt. Per watt is the unit that you measure solar in. And 2015 is down to 30 cents a watt. So if you work that out, you're talking about it's 99.99% cheaper than it was in the 1950s. So the price is just absolutely tumbling. When I was doing solar, we had the feed-in tariff, and it was to incentivize people to put solar onto domestic properties and commercial properties and schools, etc. And the government kept on decreasing it. They got the pricing wrong a couple of times, got the industry it crashed the whole industry. But now, for the first time ever, they've had the first unsubsidized solar park go in the UK. So that means the price of electricity being produced by solar is cheaper than fossil fuels, which is actually a game changer. We could actually see in a very short time actually solar just like becoming the most dominant form of energy in probably about 3/4 of the countries in the world that have a bit of higher solar radiance, and it's happening. So all we have to do is figure out clever ways of storing it, battery storage systems. To give you an idea of the potential of solar, this is a bit of an old slide. This area here, if we covered it in standard solar panels, is enough to power all of Europe. So we could go into the Sahara Desert where there's nothing growing there, and we could grow energy and we could transport it to Europe. It's a very big ask. It would be the biggest building project in the world, but we've got the technical know-how, we've got the information to do it. Again, it's down to funding and political will if we could actually pull it off. So you get to see the different size squares here represents the total surface area. And this is based on old technology. Since then, technology has moved forward. We've got solar trackers, we've got bifacial, we've got panels that actually can work like a lot better. I'll give you an idea, again, in this country, how it works. We actually can measure very accurately how sunny it is anywhere, right down to postcodes. And we know that we're guaranteed to get here we're going to get like 1,000 watts per meter squared. That's around the London area. So you put on solar panels onto this building here. You can work out within 1-2% of the output of the system you're actually going to get throughout a whole year. It's not very sunny in winter. It's a lot sunnier in the summer because of the way that the sun rotates. So again, we have way more energy produced from solar in the summer than the winter. What you can do is you can get a roof and you can over-spec it that you actually produce a bit more excess energy in the summer. It will flatten out the curve a little bit. Instead of having south-facing panels, you can have east-west facing panels, and you get it will balance the system a lot better. Then if you have a battery system, you can store some of the energy during the day, and then you can use it at night to run your television and lights. Typical system is a house in North London. It's got 12 solar panels. They're 300 watt each. And it looks like you got your solar panels on top. They sit on top of a mounting system. You have DC, which is direct current cables coming down from it. You have a safety switch, isolators, and it goes into the heart of the machine, which is an inverter. So inverter is the only part of the solar PV system that has any kind of moving parts as such. It has a function. The solar panels themselves are giant semiconductors. They don't actually do anything. There's nothing for them to break. But the inverter, you can expect maybe to change it, once every 10 years. And it changes from DC, direct current, into AC, into alternating current. And it gets the harmonic frequency. So it gets the frequencies the same. Then it goes into here, consumer unit, and then you get to use it in your house. Any excess energy goes into the grid. We've got different types of trackers. You get ones that can actually track the sun the whole way around. It will increase the output in the northern part of Northern Europe by about 40%. A lot more expensive, but very effective. And then you have these kind of tractors, are single axis trackers, really good for areas that are near the equator, and the price again is coming way down. Future, we've got now concentrated CHP, which is you have literally thousands of mirrors, and what it does, it super concentrates all the sun into one area, into here, into thousands or so degrees. You got Pipes going up and down here to create a vast amount of steam that powers a generator. You can also store the heat from this into molten sands. So then at night you can actually then use the heat to actually generate more steam to run your turbines, and you can run them 24 hours. So concentrated CHP gets a way higher output for land use. So looking at some of the, what we could be doing in the future would be having CHP units in the Sahara Desert, and then having high density or high frequency DC cabling going to different parts of Europe and the supergrid, and you could actually link everything together, and you could, you're having everything naturally balancing the system. This is possible. They're starting to make more concentrated solar plants in different parts of the world, and they actually look amazing as well to see. So this one is in Seville. So if you're ever in Seville, you'll be close to where this is. But you need to have them when they're very sunny areas. One problem is if a bird gets near it, they actually just fry, they just evaporate because the heat's so high. Parabolic units, what they have is they have a glycol solution going in here. It gets superheated, and this then goes and drives the turbine. Something similar to this. They use quite a lot of these in the States. We're now moving towards electric vehicles. You can actually have an electrical powered car. This is a prototype. If you only drive it about half an hour a day, you can actually get all your energy without even having to plug it in. Technology is moving along very, very quick with solar. This is a house that we did in Cambridge. It's a zero carbon house. It's got 1/2 meter thick walls. We combined an air source heat pump with 10 kilowatts of solar, so 40 solar panels. This building produces enough energy per year, you work out the balance, to run a air source heat pump that heats the whole house. It heats the swimming pool, all the lights. So when you work out the energy balance, it doesn't actually require any energy to run it. It's still connected to the mains grid for winter time. This is where we need to move. Actually, I wouldn't mind moving here. It's quite a nice house. Solar panels. We are going to have tens of millions of spent solar panels in the next coming years. We're actually by 2050, I think about 10% of all the e-waste in the world is going to be solar panels. Knowing that we're going to be dealing with solar waste, we need to be putting in plants to actually recycle them, and they can be recycled. You can get them. You have to physically break them down into different components. Most of the component that goes into a solar panel is glass or glass type. There's a lot of polymers, a lot of plastic goes into it that can be used for waste energy. The copper can be recycled. The silicon itself is about 6-8% of a solar panel. That can be broken down and reformed into making new solar panels. But we need to get the facilities in place. So moving to the future, if we don't think about how we're going to deal with our waste, we're going to have a waste problem with spent wind turbines, blades, and also solar panels. Heat pumps. Some people think they're magic boxes. It's going to be one of the most important technology in the UK. So if you read the Committee on Climate Change, Zero Carbon Britain, Energy Institute, all the different publications for how we decarbonise the grid and how we decarbonise the heating systems of the country, so many of them all come back to heat pumps. And the reason being is we can't put biomass into cities and towns because we can't get enough fuel into them, and they create smoke and air pollution, and also trying to get the raw materials. Heat pumps, they run on electricity, and you can fit them anywhere as long as you got space. Great technology. They've been using them for a very long time in Germany and Sweden. 3 main types. You got air source, water source, and ground source. It's a project in Dublin in Ireland. It's a nursing home where we used 6 air source heat pumps. How it works, I'm going to start off with the collectors first. This is a ground source heat pump. You have collectors, you have a glycol solution, which is like antifreeze and water. And this goes into the ground at a temperature of like -2 degrees. And the ground temperature is a constant temperature of about between 9 and 12 degrees, depending which part of the country you're in, and depending what type of the soil it is. Every year, with rain and solar energy, it replenishes the heat in the ground. So what you're doing is you're extracting a little bit of heat from the ground, it goes down nice and cool, and then by the time it comes up, Glyco Solutions heat it up a couple of degrees. And collectors, you've got horizontal, they just go forward and back. You've got slinky, they're kind of in loops. You've got water, you can actually go into a pond, which actually works a lot better, and you got open loop. And this here is a air source heat pump. It actually gets the energy from the air. So it works on the same principle, but it actually sucks air in, and that's where it gets its latent heat. So how it works is always very hard to explain. Everybody here probably has a heat pump in their house. It's a fridge. So you stick something into a fridge nice and warm, you close it, you come back several hours later, you open it, you take it out, and hey presto, it's cold. So it's a magic box as well. How it works, you've got your collector here. So you've got the, as you pointed out here, you've got your collectors here, you've got your ground source, water source, and air source collectors, which is this bit here. So it goes out into the environment, it comes down, it collects a couple of degrees of heat from the air, from water, and then it comes back into the heat pump itself, and it comes in contact with a refrigerant gas, and the refrigerant gas has a boiling temperature of about -27 degrees. And so when it comes in contact, you get a transfer of heat from this loop here, and it goes into the evaporator. When the refrigerant gas heats up from -27, its boiling point is -27, it turns from a liquid into a gas. So you've transferred the energy from the liquid into the gas, and it goes into a compressor. You need electricity to run the compressor. It spins around and it compresses the gas, and when it compresses the gas, it heats up. So it's like if you go on a cold day, you get a bicycle pump. You get a bicycle pump and you're pumping air, and next thing your hand starts getting warm. So it's Boyle's law. So it's as a gas compresses, it actually heats up, and it heats up to 60, 70 degrees depending on the type of heat pump and depending on the refrigerant gas. Then it goes into a condenser. It expels the heat, so it goes into another heat exchanger. So this part here is a heat exchanger, and it exchanges the heat from the condenser into the distribution system. It's going to go back one slide, and that then heat ends up here in a nice big tank. And then your heat distribution system is, it can be underfloor heating. So if you've got a big area of underfloor heating, you'd have the heat coming out at about 35 Celsius, and then the returning temperature is about 27 Celsius. So it's very low grade heat. So what a heat pump is doing is moving low grade heat, is compressing it, and then moving that compressed heat to a different place where it's been moved. So a heat pump is actually, it's a heat transfer machine using refrigerant gases, very, very clever closed loop refrigerant gases. Once the latent heat's been given off, the refrigerant gas cools back down again. It goes into an expansion vessel, which then puts it back into the evaporator, and then the cycle continues. So you've got this continuous cycle going on. So the hard thing about heat pumps is getting the sizing right. If the size is too big, your heat pump is not going to be running very efficiently. If you got it too small, it's not going to have enough heat to actually heat a building. And then to heat a building, it needs to have a building that has a certain amount of air tightness. So if you put a heat pump into here and you've got single glazed windows and you've got a draft coming and going, a heat pump wouldn't be a very efficient way of actually heating a building like this. So the first thing you need to do is you need to increase the thermal insulation, and you need to increase the air tightness. You can retrofit, you can do large scale retrofits. This is a hotel in Wexford in Ireland. It's a 107 bedroom luxury hotel with got a spa, swimming pool, and the whole place is run using 3 60 kilowatt heat pumps. So you can actually keep on joining them together to get enough energy that you need. Then the whole hotel, all the radiators were replaced with smart radiators. They're called smart rads, and they only use about 5% of the liquid that goes into a traditional radiator. And then you've got a fan at the back that actually gets the heat out of it, so you can get a radiator with like 35, 40 degree flow temperature to heat a room. It's all very clever stuff. To give you an idea, give you a comparison to what we're trying to change over from, gas boilers running on natural gas, we need to try and get off natural gas and get onto heat pumps. Problem with heat pumps is they're expensive. The actual units themselves cost a lot of money. To retrofit, you need to put in additional piping, you need to put in a buffer tank, you need to put in a new type of cylinder. So this all costs money compared to a gas boiler. The running cost, once you get a heat pump up and running, its running cost is quite low because every kilowatt of electrical energy you put into it, you get 3 to 4 kilowatts of heat energy out. So this is the magic part of a heat pump. The fuel is electricity versus gas. Maintenance, it's like a fridge. How often do you need to fix your fridge? Not very often. So it's the same thing, a gas boiler, they break every 8 to 10 years and need to be serviced quite a lot. If you get clean energy going into them, they're actually 100% carbon neutral. That's why we're relying on meeting our future zero carbon Britain by using heat pumps. That's air source, water source, ground source, bivalent systems where we actually will combine 1 or 2 technologies to get the best use out of them. Some of the problems we've got, capital costs. Most buildings in the UK won't be suitable for them because they're not warm enough. They need to actually have the energy efficiency improved first. The design is a big problem. You can't just rip out a gas boiler and stick in a heat pump. You have to do heat loss calculations, which cost a lot of time and money. There's limitations on the grid as well. If you put in a big commercial heat pump, it needs a certain amount of energy to actually get it started. So moving to the future, we're going to have to look at increasing the grid capacity for heat pumps and also increasing for electric vehicles. Other big problems that most people don't know, it's got the hydrocarbons, the F-gas that we talked about. Most heat pumps have a little amount of F-gas, which are 23,000 times more potent than CO2 in it. If anything happens to it, it gets into the atmosphere, you've ruined everything, the advantage of having a heat pump. Luckily, we've got very strict F-gas regulations in place in this country to actually deal with that, and people have to be highly trained to actually use F-gas and their homogeneity seals. So not too much of a problem. And the other biggest problem we have is lack of trained installers. We've had people, subcontractors coming in, and they put buffer tankers on the outside, which means the heat pump's never going to work. And we've gone to some places where we've had traditional plumbers plumbing the system as you would radiators, and it's not going to work. So a lot of design and thought needs to go into them. If you get it wrong, ground source heat pump, it can extract so much energy from the ground, it actually physically freezes the ground. And the other way you get it wrong, and then you've got a machine that's actually not running very efficient. But once it's up and running, no maintenance costs, they last a very long time, proven technology, they're very safe, and also there's no combustion going on inside them. Biofuels, biomass, biogas, we use a lot in this country. Solid waste, we burn rubbish, it's not a very good source of energy. We've also produced fuels from biogases as well. In the future, quite a lot of the UK energy mix is actually looking at using biogases and biofuels. So it's a technology we need to keep an eye out for. One of the things about anything is it produces waste, it produces methane, or it produces carbon dioxide. It's part of a carbon cycle. It's claimed to be carbon neutral. In the olden days, the whole world was carbon neutral. People go and they chop down a tree, light a fire, cook. A couple of years later, 20, 30 years later, a tree grows back and they cut it down again. Now we've got a huge population in the world. We haven't got enough trees, we haven't got enough biomass. It's not the answer. In this country, we had the likes of some power stations. They converted to biomass, the Drakes, and they were actually importing wood from America. A lot of the wood they were importing, it turned out it wasn't actually sustainable as they were claiming it to be. And once you start working out the true carbon cost, it wasn't actually as green as people claimed it was. If it's used correctly and you've got certain types of rotational crops, it can work brilliantly. If you do it wrong, it's adding to the problem of the environment. Quite simply, you've got different wood fuels. You've got rubbish, which we use a lot in this country. We're actually building more incinerators, which I'm totally opposed to. You've got alcoholic fuels, you've got crops. Miscanthus is a very fast rotational crop in zero carbon Britain produced by CAT. They talk about like changing land use and actually using fast rotational crops, which seem to work quite well. Also then you've got some biogas produced by landfill and methane, and they actually stick pipes down and they extract the methane and they burn it. Used correctly in a lot of countries, it's great because it gives off a vast amount of heat. You inject some air to the back of it, and it super burns the emissions, and then you can put scrubbers on the waste air coming out, and it actually cleans it up as well. So done right, it's quite good. Not done correctly, it's absolutely awful. Solar thermal, probably the simplest renewable technology. What you're doing is you're getting solar irradiance. It doesn't actually have to be direct sunlight, it can be warm air as well. You've got these collectors up here. These are evacuated tubes. They're a sealed unit. It's glass on the outside. Inside you've got black strips with some foil, and then you've got a glyco solution that goes in and out of the plates. And then some of them you've just got a heat transfer system up here where again the glyco solution touches the plates and it transfers the heat. It superheats it to 180 to 220 degrees Celsius. So you need to have special pipes connected. When you put this in, you can't use ordinary copper pipes, and you can't use ordinary welding. Countries like Israel, it's actually compulsory to have solar thermal. You go to Greece, you go to Spain, and they've got nice simple ones where they got the collector and they got the tank sitting right beside it. Nice and simple, throughout the day, heats your hot water, and then you get to use it. More modern ones, you can actually use these to actually preheat hot water for a heating system. So it works quite well. You can actually combine them with heat pumps. So you preheat your hot water with solar thermal, and then next thing your heat pump kicks in and it uses the preheated water as an energy source. In Denmark, they've even gone one step further, and instead of putting one or two of these on top of a building, they put hundreds into fields, and they have these giant water tanks built on their buildings, and then they use that to actually heat buildings during the winter. All right, very, very simple technology. Works really well. In the UK, you're going to be competing for roof space if you're retrofitting residential property, but you only need to have one or two solar thermal collectors for 4 to 6 people in a house. So you don't actually need that much roof space. It's uneconomical if you've got only one person or two person in a house. It doesn't really make sense to have it, but if you've got a family, it's a great technology to have. Very little that can go wrong with it. Leaks is a bit of a problem. If it leaks, you've got a glyco solution that leaves a bit of a pink stain in places. But apart from that, once it's up and running, yeah, brilliant. Hydropower. It's indirect from solar energy, from the water cycle. So we get formation of rain falls, gravity into rivers, and you get an area that's dammed, builds up a big pressure of water, and you use big turbines to use the energy from it. This is a place I went to in Brazil. I think it's the second largest hydro plant. You can see there's all these here, and there's only one of them open, right? And the reason being, this whole hydro plant that's damming the San Francisco River in northeast of Brazil is running on 22% capacity because of drought. In Brazil, they're having huge energy problems because of the change of rainfall, and they've relied so much on hydro, and it's now proving to be unreliable because of changing patterns. But once they're up and running, they produce vast amount of energy, but they also have vast amount of problems. How it works is quite simple. You've got 3 different types. One is you dam the water, you physically block the water, it builds up a artificial lake, and then you've got a controller that you can open and close. Intake comes in with the pressure of water, it goes into a generator, drives a big massive turbine. These turbines can be like 3 to 5 meters across, absolutely huge. And they produce vast amount of energy. The biggest power plant in the world is the Three Gorges Dam in China. It's so big that they had to, I think, rehouse over 1 million people. Vast amount of destruction. It dams so much water that it actually has slowed down the rotation of the Earth by like a nanosecond. So it's like an ice skater. When an ice skater is spinning around, you got the hands out, it goes slow, and then you pull the hands in, it goes quicker. So literally, they've shifted that much water up a little bit that it's actually affected the rotation of the Earth. So you've got 3 different types. You've got impounded, run-of-the-river and pumped storage are the main 3. And then you also got some micro hydro, which actually works quite well on small little rivers. Big problem with hydro, if you've got a drought, they're not going to work very well. Huge environmental damage in hot regions because dammed water, it stops debris. Debris and silt builds up. It forms methane. Vast amount of methane is actually released from hydro plants. So much so that the IPCC is actually going to change how it does accounting for hydro. And that's why hydro is counted different to all different renewable technologies. And also huge amount of damage for fish stock and population. And also then building it as well, the likes of some of the latest dams in Brazil, they want to build. It involves literally destroying vast areas of pristine rainforest and vast amount of concrete. Amazing technology. It produces more renewable energy at the moment than any other technology in the world, but it's kind of coming of age of actually how we actually use it. The preferred technology is run-of-the-river, where you don't dam a whole river. What you do is dam or you siphon off a part of it and redirect that to generate electricity without upsetting the rest of the river flow. Tidal energy, absolutely amazing. Every day the tides rise and fall in this country and everywhere around the world. It's predictable, moving vast amount of energy. Seawater is 832 times denser than air, so it's got over 800 times more energy in it. With tidal, you've got 3 different types. You've got tidal streams, which is very similar to hydro, same types of turbines. You got tidal barges, and then you got tidal lagoons. A tidal lagoon, you might have heard of Swansea Bay. Every couple of years, they talk about putting a tidal lagoon in Swansea Bay. It got voted down again, saying it's too expensive and it's too environmentally damaging. After doing a bit of reading about it, it's a little bit questionable, really. If you put in Swansea Bay and the Cardiff Bay, it would produce probably, I think, about 7-8% of the electrical needs for the next 120 years in the United Kingdom. Vast amount of energy. It's predictable. You know when your tides are going to be. You get to produce energy 4 times a day. 2 tides going in, going out. And the United Kingdom, so I'll say British Isles, so also has Ireland in there, has the 2nd highest tidal range in the world of 14 metres in the Swansea Bay, which is astronomical, really. So if you can dam that, or you can siphon off some of the energy from it, it's a vast amount of energy. The payback time is so great. Within the first 6 months, it's actually paid for all the embedded energy for the next 120 years. So in terms of energy payback, you cannot get much better than tidal lagoons. So these are some of the different designs we got going on here. You can actually go and create an artificial lagoon. Then what you do is you put in turbines that control the flow of water going in and out twice a day, so 4 times a day producing energy. Moving to the future, then you can even cover the whole lot with solar panels. And if you have standalone units, you can actually then split them, that you can actually have them for repairing them at different times. And this is a typical tidal lagoon proposal. I think there's about like 6 areas in the UK they're looking at putting these. But again, it got shelved by the British government because they're saying that the energy was too expensive, and it comes down to it's called the strike price. So how much you pay per unit of kilowatt or megawatt of electricity. So to give you an idea, the government said it was £150 per megawatt strike price, which is very high. But if you average it out over 60 years or 120 years, the actual price comes down quite a lot. So it depends on which way the accounting was going on. Deep geothermal. In Cornwall, they're starting to use deep geothermal, which is you get a giant drill and you just keep on drilling and drilling and drilling down 3 or 4 kilometres. Then you put pipes down, you put water down, and then the water comes back up and the water temperature is raised, and you use superheated water to power turbines. Very simple. The hard part is actually the drilling down and the engineering that's going into it. Once it's up and running, fantastic amount of energy you can get from the ground, but there's only certain places you can actually use this type of technology. So it has to have certain type of rock, and it has to have certain characteristics that you can actually use deep geothermal. Where deep geothermal is actually used quite a lot is Iceland, New Zealand, Indonesia, Japan, anywhere where there's volcanic activity, where it's quite close to the surface. But again, there's only a certain amount of energy you can get out, because even that needs to replenish its heat. And the future, smart grids. All this intermittent energy that we're going to be producing, what we need to do is we need to balance it with our energy needs. So on a very simplistic level, we've got things called microgrids. So microgrids, you start putting them in Africa, where you have a school, a community, you have like 5-10 houses, and what you do is you put in a solar PV system and a battery storage system and a small little wind turbine, and all the energy you get, you use. When you run out of energy, you have some in your battery, and when you run out of that, you have a couple of hours with the lights off. Moving to the future, smart grid, what you're going to do is you're going to have a look at all the electrical appliances you have in your house. So you got things that you don't use very often, like your fridge freezer. You might open that maybe once a day, maybe once a week. Your fridge you open maybe 3-4 times a day. So you've got these electrical appliances in your house that you don't actually have to run all the time. And soon we're going to have these big, huge batteries attached to houses that we don't need to have running all the time, which are going to be electrical vehicles, which draw down vast amount of energy. And then we're also going to have computer screens. We're going to have all these different things that we use on a daily basis. And the smart grid, it talks to each other and it figures out energy use. Peak energy times is between 6 and 8 p.m. You come home, come back from work, all the lights go on, the TV goes on, the kettle goes on, and all of a sudden we have these big, huge peaks in electricity. And this is the problem with trying to balance intermittent energy supply. So what we need to do moving to the future is having smart grids where different appliances, different industries as well, so heavy electrical using industries, when the demand increases, they start switching off different areas. So it's all done by grid monitoring that goes on, nice and complicated, that actually manages everything. This is where computer whiz kids come in. Here we've got solar, you've got wind, and then it's going into your smart home with your little micro electricity that you're generating yourself. You got plugged into your smart car, everything's talking to each other. So this is the whole concept of a smart grid. And you tie it into interconnectors with different countries, and you got from a national grid to an international grid, and then you're starting to create kind of super grids. This is where we're moving to the future. If we can crack battery storage or storage of energy, this will work quite well. This country relies heavily on nuclear energy. This is the most expensive building in the world, so the price tag of about 26 billion so far. That's not including the decommissioning, and I think another 7 billion for decommissioning. I'm not too sure on that figure, but it's 26 billion. It's a joint venture between EDF and the Chinese government are actually paying for this. We pay for it by strike price of electricity, which is £92.50 per megawatt hour, which is very expensive. Okay, so offshore wind is a lot cheaper. Onshore wind is about 3-4 times cheaper than that again. So renewables is actually cheaper than most nuclear. But what it does give you is one single building like this gives you such a vast amount of energy that it's like 4 or 5% of all the electrical needs of the whole country comes from, like, you know, one building. You put uranium in there, and through a very complex atomic process, you get a vast amount of energy. Again, drives turbines, which creates electricity. The disadvantage is you can't switch them on and off. You got problems with nuclear waste. You got problems of actually getting enough uranium. You got the build cost. So everything has a plus and minus to it. The governments here in the UK, all the future plans all relies very heavily on nuclear. A lot of nuclear plants are going to be decommissioned, and there's a lot of plans to build a lot more nuclear. There's even plans in place to build small thermal nuclear reactors, which are kind of like reactors that you get in nuclear submarines and nuclear ships, and you can have them in towns and cities around the country. So that's one technology looking at the future. This is uranium, third generation. The ones of the future, we could have thorium, which has a lot of added benefits, a lot safer, except we haven't cracked that technology yet. And again, I think we're about 10, 15 years, maybe 20 years away from thorium reactors. So there's a big question about nuclear. If you go and get rid of nuclear, what are you going to replace it with, is pretty much the question. Carbon capture and storage, I call this the unicorn technology. Our fourth and fifth carbon budget in the United Kingdom is all based on carbon capture and storage technology. The reason that we're still extracting fossil fuels is because of carbon capture and storage technology. I think it's 1.7 trillion since the Paris Accord has been signed, has been put into extraction of fossil fuels. What they're claiming is that we're moving towards using carbon capture and storage technology so we can continue burning fossil fuels. There's only a couple of plants around the world that they've tried. It does work. They haven't tried it on scale. It's very, very expensive to do. There's three main types: post-combustion, pre-combustion, and oxy-fuel. I don't know too much about it, but one's extracting the carbon before you burn it, the other one's extracting the carbon after you burn it, and the other one's using kind of some oxygen type process to burn it at a different rate. Again, our whole future is actually now relying on this technology. So airport expansion, the reason we say we're going to reach zero carbon by 2050 is because of carbon capture and storage. And I'm not an expert on it. I can't comment too much about it, but from just reading about it, it just sounds like it's too much to kind of like put the future of the world into technology that hasn't been proven on scale that's actually needed. And the actual cost of retrofitting all our thermal plants, is about £1 billion per plant. So it's very expensive, it uses a vast amount of energy. The other one that we're looking at is bioenergy carbon capture and storage. This one comes up of using fast-growing crops and again using a process of extracting the energy, changing it into a biofuel, synthetic fuel, and you burn it, and then you bury some of the excess carbon. So again, I don't know too much about it, but I do know it's unproven at scale, and we're relying very, very heavily on this in the future. So it's something to be aware of and become opinionated about. I'm coming towards the end now of where we start tying everything together. This here is from our friends in the Business Energy Industrial Strategy. This is looking at the future costs of energy. What we've got here, we've got our main renewable sources in the UK, which is onshore wind, offshore wind, and large-scale solar. Then we've got our traditional fossil fuels, and then we've got nuclear. Blue is the development costs, so pre-development cost of actually designing a system. Pink here is the O&M of what it actually takes to run the system. Then you've got your fuel costs, construction costs, decommissioning. So it's the life cycle cost of a plant. So you work out everything from concept to building it, to putting energy in to run it, to decommissioning it and starting again. And you end up with this, it's called levelized cost of energy, and it's a very good way of comparing different energy sources. What we've got here is we've got nuclear. So this is the new water reactor that's going on. I think FOAC, it hasn't been tried before, so it's new technology. There's no case study that they can work from. Then you've got coal. Again, this is coal here, and this is coal combined with CCS, which is carbon capture and storage. This is a gas combined again with CCS technology. Then you've got coal again. So you've got your different types of coals, and this is a fast reactor as well. So what you can see here, quite simply, your renewable sources are actually cheaper. This is quite a big major game change. Fossil fuels are now more expensive than renewable energy. And we've never had this before. We've always relied on subsidies, And as solar gets cheaper, the levelized cost of solar is going to be reduced with offshore wind as well. Once they get interconnectors in place, again, the price is tumbling down. One other game changer we're going to have is hydrogen. Everything comes down to balancing the grid. With an intermittent energy supply, if you overproduce wind and you overproduce solar, if you have somewhere where that excess energy can go to, such as pump storage systems, smart grids, electric vehicles, but the future, I think, is a lot of it's going to rely on hydrogen. And you can use that excess amount of energy using electrolysis, split water, and you've got hydrogen that you can store. Once it's stored, then you can actually use it sometime in the future, produce energy, and you can actually also use it at the same time for driving cars, or driving heavy goods vehicles, vans, trucks. So it's definitely a technology of the future. So combining intermittent supply of renewable energy, pump storage and hydrogen and a smart grid, we can actually we can get 100% renewable energy to run the country. There you go. Thank you. Whiskey time.